Salam, peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Part 14. Knots and braids as word formation. Remember the language we are learning. There is one field, phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once. Time as omega, space as k, and motion as v, built from both together. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and a motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes. We are in Episode 8, the pure abstract language. We are deep in Book 8.4, Abstract Topology, where we focus not on forces or equations, but on the shapes that phi can tie into itself. We have already met the grammatical boundaries, the sigma set, where smooth description tears. We have seen how winding numbers emerge from loops, how walking around the defect and counting the turns of phase produces discrete integers from a continuous field. That was our first glimpse of how counting arises from continuity. Today we climb one level higher. We will see how these simple topological ingredients, sigma lines and winding numbers, can combine into structures of astonishing richness. In ordinary language, letters combine into words, and words combine into sentences and stories. In the holophase language, sigma lines and their windings combine into knots and braids, topological words written directly into the fabric of space and time. Our aim in this part is very simple. By the time we finish, you should be able to look at tangled patterns in the world, in fluids, in fields, in DNA, in traffic, even in the stories of people, and feel in your bones that these are not just accidents. They are topological words, written in a single continuous language. Let us begin gently. Imagine you're holding a single piece of string in your hands. You join the ends so that it forms a loop. If you place it on a table without crossing it over itself, you have the simplest possible closed curve, a circle. In the language of topology, this is a very special object. You can stretch it, squash it, tilt it, make it longer or shorter, but as long as you do not cut it or glue parts together, it remains the same topological type, an unknotted loop. Now imagine instead that before joining the ends, you tangle the string around itself in 3 dimensions. You pass one part over another, then under, then over again, and finally glue the ends together so that the tangle is locked in. If you now place this loop on the table, it may look messy, but something important has happened. No amount of gentle pushing, pulling, or straightening will turn it back into a simple circle. To untangle it completely, you would have to cut the string. You have created a knot. In the language of holophase, imagine that the string is not a physical rope, but a curve drawn along the set sigma, the set of points where our smooth description breaks down, where phase value is undefined, or where its derivative blows up. A simple circular defect line is like an unknotted loop of sigma. A knotted defect line is like that tangled piece of string, a sigma loop tied around itself in 3-dimensional space in a way that cannot be undone by smooth deformations. Already you can feel the difference. A simple loop is a kind of topological letter. A knotted loop is more like a word. It carries extra structure, extra information, encoded in how it is tangled. From the time perspective, a knotted defect line is like a recurring motif in music, a phrase that appears again and again, recognizable even when played in different registers or by different instruments. The exact positions of the atoms making up the defect may change. The local fields may vibrate, but the overall pattern of linking and crossing remains the same. The knot is a stable temporal signature. From the spatial perspective, the knot is a complicated 3-dimensional shape carved into the fabric of space. It defines an inside and an outside, a core and a surrounding region. Its crossings and loops create tunnels and channels for fields and flows. The exact distances and curvatures can change, but the pattern of threading, which loop passes through which, persists. From the motion perspective, the knot behaves as if it possesses a kind of topological inertia. You can push it, shake it, move it through the medium, but unless you pass it through itself or through a boundary, its tangle does not disappear. It resists being undone. It has a stubbornness that is not due to energy barriers alone, but to the structure of space itself. So a knot is already a complex word in the holophase language. It is a closed loop of sigma whose embedding in space carries non-trivial topological information. Now let us let time flow. Instead of looking at a single snapshot of space, imagine watching the evolution of several defect points in a plane. At one moment, you see 3 points. At the next moment, they have moved slightly. Over a long period, they dance around each other, sometimes approaching, sometimes separating, sometimes looping around in intricate patterns. If you take these time-dependent positions and stack them into a three-dimensional picture, with time as the vertical axis and space as the horizontal plane, you will see a set of threads rising upward. Each defect traces a continuous line through time. Where two defects swap places or circle around each other, their world lines cross in this space-time picture, going over and under in a way that looks like a braid. This is our second object, the braid. Braids are histories. A braid is not just where defects are at one instant. It is the record of how they have moved relative to each other over an interval of time. Each crossing in the braid diagram tells you that one defect passed in front of or behind another. The order of crossings matters. Two braids with the same starting positions and the same ending positions can be topologically distinct if the sequence of over-under moves differs. You cannot continuously deform one braid into the other without letting strands pass through each other or reversing the crossing order. In the holophase language, braids are like verbs and clauses. They tell you not just what exists, but what it has done. Who moved around whom, in what order, and with what relational effect. Let us read their three echoes as well. From the time perspective, a braid is literally a picture of temporal sequence. Each crossing is an event in time. One entity passes another. The vertical direction in a braid diagram is time itself. When you read a braid from bottom to top, you are reading the story of interactions. From the spatial perspective, each horizontal slice through the braid shows you the arrangement of defects at a particular moment. If you freeze time, you see points in the plane. If you slice slightly higher, you see where they are a little later. Spatially, braids are families of configurations stitched together. From the motion perspective, a braid is the distilled essence of motion as relation. It ignores absolute positions and focuses entirely on who weaves around whom. It is motion stripped down to its relational skeleton. The exact speeds are not recorded. Only the pattern of exchanges matters. Knot and braid together give us the basic topological vocabulary of holophase. A knotted sigma loop is like a noun phrase, a stable entity with identity. A braid of sigma roll lines is like a verb phrase, an interaction history between entities. Now we add grammar. How do we know when two loops are truly linked? How do we decide whether a tangle is one word or two? In ordinary language, grammar gives us rules about which words can follow which, how they agree in number and tense, and how they form larger structures like sentences and paragraphs. In topology, an important part of this grammar is encoded in numbers called linking numbers. Imagine two loops of string floating in space. If they are far apart and do not intersect, you can imagine shrinking each one a little, moving them gently, and separating them completely. In that case, we say their linking number is 0. They are unlinked. Now imagine two rings, like wedding bands, interlocked. You cannot pull them apart without cutting one. If you look at them from the right angle and count how many times one passes through the hole of the other, you will find that they are linked once. Their linking number is 1. With more complicated links, this number can be higher. In the holophase setting, the loops are not pieces of metal, but closed sigma curves, the curves where our smooth phi description fails. The linking number tells us, in a precise way, how many times one defect loop threads through another. It is a discrete relational label, just like the winding number. But now it measures relationship between loops rather than winding of phi around the circle. Linguistically, linking numbers are like relational grammar markers. They tell us which words are tied together and how strongly. Two particles might each carry their own winding number, their own charge, but they can also be linked, their histories intertwined in a way that cannot be removed. The linking number is then a topological marker of that relationship. Put all this together, and a picture emerges. At the base, we have phi, the continuous cyclic field. From it, we grow derivatives, time derivatives, space derivatives, mixed derivatives, forming the master tree. These describe local behavior: slopes, curvatures, accelerations, convergences, shears, twists. This is the smooth grammar of the language, the way phi changes in each tiny neighborhood. On top of this, we have topology, the study of global shapes and connections that survive all smooth deformations. Sigma marks the places where the smooth description breaks. Winding numbers count how many times phi wraps around its circle as we loop in space or time. Linking numbers tell us how loops of sigma wrap around each other. Knots and braids are the complex configurations formed when many loops and lines of sigma tie together in space and time. You can think of the master tree as the grammar of local sentences, and the topological structures as the paragraphs and chapters, larger scale units of meaning that persist and interact. Now, why should we care about knots and braids, beyond the beauty of the picture? Because in many areas of physics, these are not remote abstractions. They show up directly in experiments and observations. In fluids, for example, vortex lines, places where the flow speed becomes singular or undefined, can knot themselves. In superfluids and superconductors, the phase of the order parameter plays the role of phi. Defects in that phase can form loops and braids. In optics, lines of zero intensity in complex light fields can knot into intricate patterns. In all these cases, the stability of the structure is not due to the stiffness of a material, but to the topology of how singularities are arranged. In condensed matter physics, braiding has become central in the study of exotic quasiparticles called anyons. In certain two-dimensional systems, when you move one anyon around another, the quantum state of the system changes in a way that depends on the braiding pattern, not just on final positions. The world lines of the anyons in spacetime form braids, and the quantum mechanical phase acquired by the system is a representation of the braid group. This is not metaphor, it is laboratory reality. Topological quantum computation is built on this principle, using braids in configuration space as operations on quantum information. In biology, DNA often ties itself into knots and links. Enzymes have evolved specifically to cut, pass strands through each other, and reseal them, changing the topology of the DNA. The functioning of the cell depends on these controlled topological operations. The DNA is not just a chemical chain, it is a topological object with knots and links that matter. In chemistry, researchers have learned to synthesize molecules shaped like knots: trefoils, figure-8 knots, and more complex links. Their stability and properties depend not just on the chemical bonds, but on the topological form of the molecule, how the backbone is threaded through space. In all these examples, Holophase sees a single pattern. Phi, or a phi-like quantity, has defects. The defects form loops and lines. Those loops and lines knot and braid. The resulting topological words are stable carriers of information and structure. This leads us naturally to a falsifiability question. The Holophase program makes a strong claim that many, perhaps all, of the stable, discrete structures we see in nature can be understood as topological words in a phi language. If this is true, then whenever we find a robust, long-lived structure, a particle, a vortex, a soliton, a protected edge mode, we should be able, at least in principle, to describe it as a knotted or braided configuration of defects in a phi-like field. To test this, we can ask, are there observed phenomena that clearly require topology, and do they fit the knot and braid picture? In many cases, the answer is already yes. Quantized vortices in superfluids, flux tubes in superconductors, skyrmions in magnetic materials, anionic braiding in quantum Hall systems. Each of these can be drawn, at least schematically, as knots and braids in an appropriate order parameter. Falsification would come from the opposite direction. If we discovered stable quantized structures whose behavior utterly refused any topological interpretation, whose stability and interactions depended only on some non-topological algebraic scheme that cannot be realized as the topology of a field valued in a circle or a related space, then our claim would be in danger. The holophase language would no longer be a universal script. It would be one dialect among others. This is good. It means knots and braids are not just poetic images. They are scientific commitments. They can be right or wrong. If you want to see the more formal side, braid groups, knot invariants, homotopy classes, and how they appear in phi-based models, you can search for holophase on Zenodo. There you will find the scientific papers that this audio journey is built on, with equations and diagrams that show the precise mapping between defects in phi and elements of these topological groups. For now, stay with the images. Think of a tangled pair of headphones in your pocket. When you pull them out, you do not see a smooth circle. You see loops pass through loops, knots that hold even as you shake the cable. That is topology in your hand. The particular pattern of crossings and loops is a topological word. You can spend minutes performing a kind of local topology, passing one part of the cable over another, trying to reduce the tangle to a simple loop. Sometimes you succeed. The knot was only apparent, not topologically real. Sometimes you do not. Somewhere, there is a genuine crossing that you must open by pulling an end through a loop. Or think of a maypole dance. Children or adults stand evenly spaced around the pole, each holding a ribbon attached to the top. As music plays, they walk around the pole in choreographed patterns, weaving the ribbons over and under each other. At the end, the pole is wrapped in a colorful braid. That final pattern is a physical record of the braid in time, a static image of a dynamic topological word. Or think of rivers on a map. Where two rivers meet and twist, they can wrap around islands, carve channels that reconnect downstream, and sometimes braid into complex patterns. From above, the channels look like strands of a braid, dividing and rejoining, weaving a history into the landscape. These are all analogies, but they help you build a practical recognition skill. When you see persistent tangles and weaves, structures that cannot be undone by small, smooth nudges, you are seeing the shadows of knots and braids. Bring this back now to the core of our journey, phi itself. Knots and braids are not extra substances added on top of phi. They are not additional stuff. They are particular configurations of phi's own failure to be smooth. They are patterns in the sigma set and in its evolution through time. The field is still one. The tapestry is still continuous. The embroidery, the knots and braids, are simply regions where the tapestry folds, loops, and threads through itself in non-trivial ways. Zoom out with me for a moment. Remember, everything we have talked about is still just one field, phi, and its derivatives. The single language the universe uses to write every story. In Episode 8, we are stepping back from any particular universe and studying this language in its pure abstract form. We have met phi as a function into a circle. We have met shift symmetry, which says that only differences in phi matter. We have met sigma, the grammatical boundary where smooth description fails. We have met winding, where integers arise from loops. And now we have met knots and braids, complex, stable words made from these simple ingredients. In the chapters to come, we will introduce one final topological concept, holonomy, the way in which even a path that looks trivial can pick up a hidden phase when there is curvature or connection in the background. Holonomy will tie topology back to the derivative structure of the master tree, showing how local curvature and global loops speak to each other. It will be the bridge from pure topology to gauge theories and quantum phases. For now, I invite you to walk through your day with new eyes. When you see the braid of hair on someone's head, the weave of fabric in your clothes, the curls of smoke rising from a kettle, the winding of paths through a forest, Let part of your mind whisper. These too are topological words. They are the visible, everyday echoes of a deeper language, one in which phi and its defects write knots and braids into the fabric of existence. And remember, you are not outside this story. Your own life has knots and braids, long-standing patterns of relationship, habits that loop and twist, histories that weave people together in ways that cannot be undone by a single conversation. You can begin to see these too as topological words in a social and psychological field. This is only an analogy, not literal physics, but it can help you feel how powerful the holophase way of seeing can be. When you look at the world like this, chaos softens, tangles become messages, braids become stories, and the one continuous field, phi, reveals itself not only as motion and wave, but as grammar and text, a language that can tie itself into stable, meaningful forms. Let us deepen a little further how knots and braids sit inside the overall master tree, and why they belong to the same unified picture rather than being an ornamental add-on. At the root of the master tree is the simple fact that phi takes values on a circle. From that root, we construct derivatives: first order, second order, higher order. Each derivative asks a finer local question about how phi changes in time, in space, and along motion. The entire smooth hierarchy can be seen as a gigantic questioning machine, interrogating phi at every point. How steep, how fast, how curved, how twisted, how stretched, how coupled. Topology asks a different kind of question. Instead of asking, how steep is this right here? It asks, what is the overall shape of this entire region, this entire loop, this entire family of paths? Winding counts how many times we go around the value circle when we traverse a loop in space or time. Knots classify how closed sigma loops sit inside space. Braids classify how world lines weave inside space-time. Holonomy, which we will meet later, classifies how transport around a loop differs from staying put in the presence of curvature. Seen this way, topology is not a separate subject. It is the large-scale counterpart of local differentiation. The master tree looks at infinitesimal changes. Topology looks at global consequences. They are complementary perspectives on the same field. You can picture this in a down-to-earth way. Imagine a mountain range. The derivatives of height tell you local steepness and curvature, where the slopes are gentle, where they are dangerous, where water will accelerate. Topology, in contrast, tells you how many distinct valleys there are, how many passes connect them, how many independent loops you can walk without being able to shrink them to a point. Both descriptions are about the same landscape. One is about its fine texture, the other about its overall architecture. In the Holophase program, phi is the landscape. Derivatives describe its local terrain, and knots and braids describe its global architecture of defects. You need both to navigate. There is also a subtle but important way in which derivatives and topology talk to each other. In many physical systems, the energy, understood here as a tally of how intensely phi is changing, is minimized or stabilized by certain topological configurations. A knotted vortex, for example, may be dynamically stable because any attempt to smooth it out would require concentrating gradients and curvature into an impossibly small region. In that sense, the knot is not only topologically protected, it is dynamically preferred under the constraints of the system. This gives us a bridge between pure shape and physical law. The master tree tells us how much various derivative patterns cost in terms of our energy tally. Topology tells us which large-scale patterns cannot be eliminated without passing through high-cost regions. Together, they explain why some knots and braids in phi are not only possible, but likely to appear and persist. From the perspective of falsifiability, this interaction is crucial. It means that whenever we find a stable structure in nature, we can ask two questions at once. First, can this structure be described as a knotted or braided configuration of defects in a phi-like field? Second, does its observed stability follow from a balance between derivative-based costs and topological constraints? If the answer to both is yes, the holophase story gains strength. If the answer to both is no, the story is weakened. You can practice this mindset even without equations. When you see a phenomenon that looks stable and structured, a smoke ring, a persistent weather pattern, a luminous filament in a plasma, a spiral galaxy, a coherent pattern of traffic flow, ask yourself, is there a way to see this as a kind of knot or braid in an underlying flow field? Are there loops, crossings, and linked paths that seem to hold the pattern together? Or is it entirely ephemeral, dissolving as soon as any small perturbation touches it? Often you will see a mix. Some parts of the pattern are topologically robust, others are fragile. The holophase viewpoint encourages you to separate these, to cultivate an eye for what is structurally locked in and what is merely contingent. Let us also be clear about the limits of the analogy when we apply these ideas to human life. Social, psychological, and historical knots are not literally sigma sets in a physical phi field. They are patterns in behavior and meaning, yet they share a structural feature. Some problems can be solved by small local adjustments, while others require a radical reweaving of relationships. Thinking in terms of knots and braids can gently train your mind to distinguish between these cases, to feel when a situation is topologically entangled and when it is not. Finally, remember that every time you follow a path that loops back to where it started, every time you notice that something has returned but changed its internal configuration along the way, you are, in a loose sense, brushing against the idea of topology. Did the system come back trivially, or did it pick up a twist? Was the journey just motion, or did it rewrite the relational pattern? Knots and braids are the language's way of saying, this loop was not empty, this interaction was not shallow. Something was tied, something was woven, and that weave will remain until a truly discontinuous change unravels it deeply. Salam, and peace be upon you.